Okay, hello everyone in a new video. So we have reached part 4 of chapter 10, which is the chapter of Archimedes upthrust and the third unit of mechanics. So in this part we'll complete the explanation of this chapter. Then we have reached section number 11, which is given by flotation versus sinking of an object. So let me write here that we are in section number 11, flotation versus sinking of an object. So let's consider document 1. Here in this document we have a solid S completely immersed in a liquid. So the density of this solid is given by rho S, and the density of the liquid is given by rho L. So let me write here that consider an object S of density rho S. So rho is the density of the solid. It carries the subscript S because it's the density of this solid, which is immersed completely in this liquid, and of real weight W. So here in this case the real weight doesn't carry a subscript R, but what I mean here by W is the real weight, which is given by W is equal to M times G. So here, because we have a liquid, we must distinguish between the real weight and the other weight, which is the apparent weight, completely immersed in a liquid L. Of density rho L. So the density of this liquid is given by rho L. Now the moment we immerse this solid S into the liquid and we leave it alone, so we expect that this solid will either float in the surface of the liquid like this, or float inside the liquid like this, or it will float to the surface of the liquid, or it will sink to the bottom of the container like this. And how do we know if it will float or sink or float inside the surface? This depends on the comparison between the densities between the solid and the liquid. So we have the solid S is of density rho S, and we have that the liquid L is of density rho L. So let's consider the first case in which the density of the solid is less than the density of the liquid. So in this case we say that the solid is less dense than the liquid. So in this case the solid is less dense than the liquid. So, or in other words, but this is not true, we can say that the liquid is more heavy than the solid. So in this case we expect that the solid S will float at the surface of the liquid. And in the case where the solid S, the density of the solid is equal to the density of the liquid, so the solid will float inside the liquid. And in the case where the solid S, the density of the solid is greater than the density of the liquid, so the solid is heavier than the liquid, then we expect that the solid will sink to the bottom of the container. So the aim of this section, or what we want to do in this section, we want to explain this, but not at the level of the densities. So what we have done in grade 7 is to check whether the solid will rise or sink using the densities. But here we need to explain this at the level of the forces in a more elegant way. And then let's say here, because the solid have a mass, then it will be directly subjected to the weight which is vertically downward. And here, because we have a liquid, then it will be subjected to the other force, which is the Archimedes upthrust force exerted by this liquid on this solid. So what's the point of application of this force? It is the center of gravity of the immersed part. So this is the immersed part because it's completely immersed. Then the center of the point of application will be the same of the weight W, which is the center of gravity of the immersed part, which is the center of gravity of S. So F will be acting vertically upward like this. Then let's say here, then the object S will be subjected to two forces, and they are given by its weight W and the Archimedes upthrust force given by F factor. And here, let's clarify from the beginning that what does this weight represent? Is it the real weight or the apparent weight? For sure, it is the real weight and not the apparent weight, although we have a liquid, but we can always speak about the real weight. And whenever we are discussing forces, we always take into consideration the real weight and not the apparent weight. Okay, so whenever we write down W as a vector, so this is the real weight and not the apparent weight. Okay, so this is the real weight. And whenever they ask us about this, the weight measured by the spring balance when the solid S is immersed in a liquid, then we can say the apparent weight. But always whenever we are discussing forces, we will mention we will be talking about the real weight. Now let's start by the first case, which is 11.1, case number 1, which is given by the density of the solid is less than the density of the liquid. So knowing that the density of the solid in this case is less than the density of the liquid, so we expect that the solid S will rise to the top. But we need to explain this at the level of the forces. So the first idea in this case, we have that the magnitude of W is less than the of upthrust. Why? Let me explain why. So knowing that the density of the solid is less than the density of the liquid and the weight is acting vertically downward like this, and F upthrust is acting vertically upward. So knowing that the density of the solid is less than the density of the liquid, so the solid S will rise to the top, it will float at the surface. So why it will rise to the top, it will float on the surface? Because the magnitude of F is greater than the magnitude of W. So F is acting vertically upward and W is acting vertically downward. Knowing that S will rise to the top because the density of the solid is less than the density of the liquid, so we can deduce that the magnitude of the weight is less than F upthrust. So then, the object start to rise. Now idea number 2. Here let me write that V represents the volume of the object, whereas Vi is the volume of the immersed part, and Ve is the volume, so this is E. Ve is the volume of the emergent part. So now after the solid S reaches the top, so now it's floating at the surface of the liquid. Now in this case, when it's completely immersed, the volume V is equal to volume Vi. When it reaches the surface, now this represents the volume of the immersed part, and this is the volume of the emergent part. So with respect to the total volume V, what does Vi and Ve represent? We know that V is equal to Vi plus Ve. So what's the type of this equation? This is a linear equation. So for example, if we know the volume V and we know the volume Vi, we can determine Ve, because now this is a linear equation and one unknown. Now idea number 2, let's say the object S reaches the surface of the liquid. So for example, the liquid in this case can be water, and it floats. As shown in document 2. So now after the solid S have reached the surface, the solid S, so in this case the solid S, when we immerse it, it wasn't at equilibrium. When we left our hand, the solid S started to move upward, to the surface, so it's not at equilibrium. But when it reaches the surface, now we can say that the solid S is at equilibrium. So here let me write idea number 3. In this case, when the solid S reaches the surface, in this case, we have so because now it is at equilibrium, we can apply the condition of equilibrium. So let's say as a title, at equilibrium. Now we are discussing document 2. I repeat, we are not discussing document 1, because yet at document 1, the solid S was not at equilibrium. It was rising to the top of the surface after we left our hand. So how do you apply this condition? Always on the left we write the sum of forces acting on the solid S, and they are given by, so here let me say that this is F upthrust, and they are given by the weight W and F upthrust. So on the left we write the sum of forces given by W vector plus F upthrust, and on the other side of this equation we write the zero vector corresponding for the condition of equilibrium, and we don't forget the vector. Now moving F upthrust to the right hand side, we can say that W vector is equal to minus F upthrust. So what do we benefit from this equation? So the first equation tells us that both forces have the same line of action, the first equation tells us that the effect of both forces acting on the solid S cancel each other to give us the zero vector, whereas the second equation tells us that both forces have the same line of action, opposite direction, same magnitude. So the minus sign is for the opposite direction. Now regarding the line of action and the direction, okay, we know that W is acting vertically downward and F upthrust is acting vertically upward, so we will not benefit anything from the line of action and the direction. However, we are interested in the magnitude. So let's say in magnitude, so here we remove the vectors, we drop down the vectors and we remove the minus sign, so we have that the weight is equal to F upthrust. And I repeat here, what does W represent? It represents the weight. So we always have two weights, either the real weight or the apparent weight. Here, because we have a liquid, it's a bit tricky. We will think that it is the apparent weight, but recall that this weight is coming from this weight vector, and from the early beginning we mentioned that this weight vector is the real weight and not the apparent weight. So this weight represents the real weight and not the apparent weight. Okay, so what do we benefit from this equation? So this is a linear equation also. So if we know the value of W, we can determine the value of F upthrust, and vice versa. If we know the value of F upthrust, we can determine the value of W. And we have an explicit formula for both the quantities. We know that the value of W is given by M multiplied by G. So for example, if we have the mass and we are performing this experiment on Earth, we can determine the value of W. After determining the value of W, we can deduce the value of F upthrust, or we can say that that the value of F upthrust is given by the density of the liquid times Vi times G. So for example, we can determine the magnitude of F upthrust using this formula. If we know the density of the liquid, for example, water 1000 kilogram per meter cube, we can measure the immersed volume and we know the value of G. So we can deduce the value of W. For example, let's say W, according to this formula, is given by 2 newtons, since W is equal to F upthrust is equal to 2 newtons. Then after we have determined the value of W to be 2 newtons from F upthrust, we can determine the value of M, because M now is given by W divided by G. So during the exercises, so basically we will use these 3 formulas in this case. Now moreover, we can ask what happened to the apparent weight. So what's the value of the apparent weight? So we can determine the value of the apparent weight, because what's the relation between W, F upthrust and the apparent weight? We know that by definition F upthrust is given by the real weight minus the apparent weight. So moving the apparent weight to the left hand side, so the minus will change to plus, so W apparent will be equal to the real weight, which is denoted by W, and dragging F upthrust to the right hand side, it will gain a minus sign, it will be minus F upthrust. But knowing that W and F upthrust are equal, so replacing F upthrust by W, or since they are equal, simply the W apparent will be 0. So here let me write that in this case the apparent weight is equal to W minus F upthrust. So from where this formula is coming? From the definition of F upthrust, because F upthrust is equal to the real weight minus the apparent weight. So dragging the apparent weight to the left hand side and moving F upthrust to the right hand side, so W apparent will be given by the real weight minus F upthrust, and the value of the apparent weight in this case is 0. So now what we have done here is discussing the case in which the solid, the density of the solid is the density of the liquid. So it's left to discuss when the density of the solid is equal to the density of the liquid, and in the case where the density of the solid is greater than the density of the liquid. So in this case, the solid S will be floating but inside of the liquid, not at the surface, and in this case, the solid will sink to the bottom of the container. So let's discuss them. Then now we are in section 11.2. So we are in case number 2. It is given by in which the density of the solid is equal to the density of the liquid. So let's say the object S is completely immersed in the liquid L as shown in document 3. For sure, the solid S here being also subjected to 2 forces, the weight which is acting vertically downward and F upthrust which is acting vertically upward. So here what do we expect to happen? So remember that we are discussing the case in which the density of the solid is equal to the density of the liquid. So the solid S will not rise and will not sink, so it will still float in the surface of the liquid like this. So what does this mean? At the level of the forces, we have the weight acting vertically downward and F upthrust is acting vertically upward, which means that the effect of both forces balance each other, which means that the magnitude of W is equal to the magnitude of F upthrust. Okay, so now we will deduce this at the level of the forces. So idea number 1, in this case W is equal to F upthrust. So the density of the solid is equal to the density of the liquid. Then the object floats in the liquid as shown in document 4. So here, because the effect of both forces balance each other, so the solid S will neither rise nor sinks to the bottom of the container. So it will stay like this. It is at equilibrium. Okay. Then directly now we can apply the condition of equilibrium, and we can say that in this case we have at equilibrium that W vector plus F upthrust is equal to 0 vector. Now moving F upthrust to the right hand side, we have that W vector is equal to minus F upthrust, and for sure we are interested in magnitude. So now dropping down the vectors and removing the minus sign, we have that W is equal to F upthrust, and for sure this weight is the real weight as we have done in the first case. So what does W represent? It's given by M multiplied by G. The value of F upthrust can be determined from the following formula, and in this case the apparent weight is given by the real weight minus F upthrust, which is given to be 0 because W and F upthrust are equal in magnitude. And here let me clarify something before moving on to the third case, which is case number 3. Here in the beginning I have said that W in magnitude is less than F upthrust. For this reason the solid S floats. Okay, but notice that here when I have discussed the condition of equilibrium, I was discussing document 2 and not document 1. Here in this case we cannot apply the condition of equilibrium. I can't say that W vector plus F upthrust vector is equal to 0. This is completely wrong in this case, because I have said that F upthrust is greater than the weight. So we have waited until the solid S reaches the surface. After it has reached the surface and being at equilibrium, it is at rest. Now in this case we can say that W vector plus F upthrust is equal to 0 vector. Okay, so here it's true that in the beginning I have mentioned that W is less than F upthrust, and later on I have said that W plus F upthrust is equal to 0 vector, but this is considering document 2 and not document 1. And here I'm considering document 1. Okay, and between document 1 and document 2 there is a state where the solid S is moving and it is not at rest. Okay, so I'm not considering this case. Now let me move to the third case, the final case in which the density of the solid is greater than the density of the liquid. So we are in 11.3, in which the density of the solid is greater than the density of the liquid. So we have the same solid here, but in this case the density of the solid is less than the density of the liquid, so we expect that the solid S will sink to the bottom of the container. So now we need to explain this at the level of the forces. So let's stay in idea number 1. In this case, or let me say that in the beginning, the object S is completely immersed in the liquid L as shown in document 5. So idea number 1, in this case W, the magnitude of W, and here by W I mean the real weight, is greater than F upthrust. Why? Because the density of the solid is greater than the density of the liquid. So why? When the density of the solid is greater than the density of the liquid, we have that the weight is greater than F upthrust, simply because. So the weight is acting vertically downward, and F upthrust is acting vertically upward. Knowing that the density of the solid is greater than the density of the liquid, so the solid S will sink to the bottom of the container. But we are interested in describing this motion at the level of the forces and not at the level of the densities. So because W is acting in the same direction of motion, which is downward, so we can say that the weight in this case is greater than F upthrust, okay? Yet we are not discussing here the condition of equilibrium. So in this case, when W is acting vertically, so W is greater than F upthrust, which means then the object reaches, then the object starts to sink. So when it starts to sink, it will reaches the bottom of the container. So when it reaches the bottom of the container, now the solid S is not moving anymore, and in this case we can discuss the condition of equilibrium. So let's write idea number 2. The solid S reaches the bottom of the container as shown in document 6. Now, because the solid S in document 6 is at equilibrium, now we can discuss the condition of equilibrium. So let's say in this case, so by this case I mean document 6. In this case we are interested in applying the condition of equilibrium. So let's say at equilibrium, now what are the forces acting on the solid S? And this is a tricky part. So we know that it's being subjected to the weight which is vertical downward like this. It is always being subjected to F upthrust vertically upward. So, and there is a force preventing the solid S from sinking down, which is the force due to this support. So this is the support. What is this support? It is the bottom of the container. And we know that whenever there is a support in contact with the solid S, then the solid S will be directly subjected to another force, which is the normal reaction. So this is the point of application of the normal reaction, because it is a contact force. So the normal reaction will be acting vertically upward in the same direction of F upthrust. So both the normal reaction and the F upthrust balance the effect of W vector. For this reason, the solid S will be at equilibrium. So what are the forces acting on the solid S? They are given by the weight. Sorry, let me say first F upthrust. So the sum of all forces, here we don't have 2 forces, we have 3 forces. And the weight, which is the real weight, plus the normal reaction due to the support on the solid S. And on the right hand side we write the 0 vector, and we don't forget vectors on all of these 4 quantities, because this is a vector equation. Now here in this case, this equation is a bit complicated. We will not discuss its we will not discuss this equation mathematically. So we will not say in magnitude. Why? Because all of the previous equations that we have discussed includes only 2 vectors in addition to the 0 vector, but this equation consists of 3 vectors. So we don't know yet how to deal with this equation, because we don't know the mathematical tools. However, what we can say is that the magnitude of the weight for sure is given by M multiplied by G, and the magnitude of F upthrust is given by the density of the liquid times the volume of the immersed part times g. And here we can also discuss the apparent weight. So the apparent weight is given by the real weight minus F upthrust. But in this case, we don't know if the real weight is equal to F upthrust here, because simply we have the normal reaction in addition to these forces. So we cannot say it's equal to 0. We'll simply say that it is different than 0. Although this seems to be a bit complicated, but as we shall see later in the exercises, they are very easy. And let's take an example, which is exercise number 8. So a wooden cube, so this is a direct application on what I have previously explained. So a wooden cube, C of side A is equal to 2 centimeters. So the side of the cube is given by A is equal to 2 centimeters. So here this is a regular shape, although they didn't mention the document, but we can use it simply because this document doesn't include any number. Okay, for this reason we can use it. So A is equal to 2 centimeters. Knowing that centimeter is not the SI unit of length, in order to convert from centimeter to meter, we divide by 100. Then 2 divided by 100, then the side is given by 0.02 meters. So knowing the side of the cube and it is classified as a regular shape, we can determine its volume. Floats on the surface of the water. Okay, given that the density of wood is given by 400 kilograms per meter cube, and the density of water is given by 1000 kilogram per meter cube. Number 1. Show that the volume of CSV is equal to 8 times 10 to the power minus 6 meter cube. This is trivial. We know the side of the cube and this is a regular shape. We can say that V is equal to 8 to the power 3. So 0.02 to the power 3. Plugging this on the calculator, it will give us 8 times 10 to the power minus 6. Since the cube is in the side of the cube is in the SI, so the volume V will be in the SI, which is meter cube. So the volume of the cube is given by 8 times 10 to the power minus 6 meter cube. Then they are telling me to show that the mass of C is M is equal to 3.2 times 10 to the power minus 3 kilograms. So knowing that the volume of the cube and knowing the density, so the mass can be calculated using the following formula. Density is equal to mass over volume. We are interested in determining the mass. So constructing the triangle of this formula, here because we have divide and rho will be at the bottom, M at the top, V here, we are interested in determining M. So M of the cube is given by density times volume. So notice that here we have two densities, density of water and density of wood. Because we are determining the mass of the wood, so we'll use the density of the wood. And the density of the wood is given by 400 multiplied by the volume of the cube, which is the wood, which is 8 times 10 to the power minus 6. Plugging this on the calculator, it will give us 3.2 times 10 to the power minus 3. Since everything in the SI, so the value of M will be in the SI, which is kilograms. So the mass of the cube is given by 3.2 times 10 to the power minus 3 kilograms. And let me say the following remark, that this is the most difficult exercises that one can face in this chapter, okay? And now you will see why. Because the value of G is not given. Now number 3. The cube is submitted to two forces, its weight W and Archimedes upthrust force. So the first thing that we must notice that what does this weight represent, the real weight and or the apparent weight. So the common mistake is that to think that this weight is the apparent weight because we have water, but this is completely wrong. And as I have said previously, whenever we have vector, we consider that this weight is to be the real weight. So here let me say that this weight vector W is the real weight to make it clear. .1. Indicate for each of the two forces if it's a contact force or force acting from a distance. So the forces that are classified as a distance are the weight, the electric, the magnetic. So the weight W is classified as acting at a distance, acting from a distance. And all other forces are classified as contact forces, and in particular the Archimedes upthrust F. So it is a contact force. Write the relation between the magnitude of these two forces. So in order to determine the relation between the magnitude of these two forces, we need to write the condition of equilibrium, which is given by let's write in, let me do 3.2 here. Let's determine first the condition of equilibrium, which is given by at equilibrium as a title. On the left, we write the sum of forces acting on the cube C. They are given by the weight and F upthrust. So, F upthrust is denoted by capital F without the subscript up. And on the right hand side of this equation, we write the zero vector corresponding for the equilibrium. And why it is at equilibrium? Because it's floating at the surface of the liquid, so it's not moving. Moving F to the right hand side, so W vector will be equal to minus F vector. The first equation tells us that the effect of both forces cancel each other, whereas the second equation tells us that both forces have the same line of action, opposite direction, same magnitude. Knowing that we are interested in the relation including the magnitudes, so let's say in magnitude that W is equal to F. So this is the relation that we are interested in. Now 3.3. Determine the volume Vi of the immersed part of the cube. So knowing that the value of Vi and the magnitude of the force F upthrust are related via the following formula, that F upthrust is equal to the density of the liquid times the volume of the immersed part times G. We are interested in determining the value of Vi. So in order to determine the value of Vi, we must know the value of G, we must know the value of rho L, and we must know the value of F upthrust. So let's check. We have the density of water to be 1000, so the liquid is water, so we know the density of the liquid, done. However, in this case, we don't know the value of G. So we don't know in which planet we are performing this experiment, okay? Moreover, the value of F upthrust for sure can be determined from this relation if we know the value of G, if we know the value of W, sorry. So W, because it represents the real weight, it can be calculated using the following formula. So we are lucky because we know the value of M to be 3.2 times 10 to the power minus 3 meter cube. However, we face the same problem, which is we don't know the value of G. Okay? But let's check how we will solve this problem. So indeed, let's construct a triangle for this formula, as we shall see that G will cancel out. So this doesn't depend on the gravity itself. So F upthrust, because we have multiply, so it will be at the top, rho L, Vi and G at the bottom. We are interested in determining the value of Vi. So Vi is given by the volume of the immersed part, which is the value of F upthrust, which is denoted by F, divided by the density of the liquid, which is denoted by rho water, multiplied by the value of G. So in order to determine Vi, we need to know F, rho water, G. But recall that the value of F is given by W, and the value of W is given by M multiplied by G. Then in this case, we have that F is equal to M multiplied by G. Now replacing the value of F in Vi, so let's rewrite Vi in terms of F, and replacing F by M multiplied by G. So it is M multiplied by G. So what I have done here is I have replaced this value in this expression, and it is the density of water multiplied by G. Now simplifying G in the numerator and in the denominator, then Vi will be given by the mass of the cube divided by the density of water, and for this reason they didn't give me as a given the value of G. And this means that if we perform this experiment on Earth and the same experiment on Moon, so the volume of the immersed part will not change, and this doesn't depend on G explicitly. Now the value of m is given by 3.2 times 10 to the power minus 3, and the value of the density of the liquid is given by 1000. So plugging this fraction on the calculator, it's given by 3.2 times 10 to the power minus 6. Since everything in the SI, the mass and the density, so the unit of VI will be in the SI, which is meter cube. So the volume of the immersed part is given by 3.2 times 10 to the power minus 6 meter cube. So VI is equal to 3.2 times 10 to the power minus 6 meter cube. Now let's compare both volumes. This is the volume of the immersed part, whereas the total volume is given by the outer volume, this, which is 8 times 10 to the power minus 6 meter cube. And for sure the total volume must be greater than the immersed volume, because there is an emergent volume. So the difference between the two will be the emergent volume, as we shall see. Calculate in centimeter cube the volume VE of the emergent part of the cube. So how do we calculate the volume of the emergent part? So knowing that we are in 3.4, knowing that the total volume and the immersed volume and the emergent volume are related via the following formula. So the total volume, the outer volume, is equal to the volume of the immersed part plus the volume of the emergent part. So V is equal to VI plus VE, knowing that we are interested in determining the value of VE. So this is a linear equation and one unknown VE. Let's replace the values. The value of V is given by 8 times 10 to the power minus 6, and the volume of the immersed part is given by 3.2 times 10 to the power minus 6 plus VE. So how do you solve this linear equation? We put VE on one side and all the other numbers on the other side. So the value of VE is given by 8 times 10 to the power minus 6 minus 3.2 times 10 to the power minus 6. So plugging this on the calculator, it will give me 4.8, I think, times 10 to the power minus 6. Since both, this is in meter cube and this is in meter cube, so the volume VE will be expressed in meter cube. So the volume of the emergent part is given by 4.8 times 10 to the power minus 6 meter cube. Notice that I didn't answer, or in other words, the unit that I have calculated. So I have calculated VE in meter cube, but the required unit is centimeter cube. So now this is simple. In order to convert from, so this is meter cube. In order to convert from meter cube to centimeter cube, we multiply by 10 to the power 6. Then the emergent volume is given by 4.8 times 10 to the power minus 6 meter cube, which is equal to 4.8 times 10 to the power minus 6 times 10 to the power 6. So it's equal to 4.8 centimeter cube. So the volume of the emergent part is given by 4.8 centimeter cube. And by this we have finished solving this exercise. So that's it for me in this video, guys. And the next part we'll complete solving exercises on what I have explained in this video.